Okay, so in this video I'm going to look at further uh, quantities in kinematics that you will probably won't ever see and use again, but may just mention them just as a bit of an exploration. So we've looked already at average velocity. It's defined as the change in position divided by the change in time. There's its equation. And velocity is said to be the first derivative of position with respect to time. So if I know the change in position, I know the time that has been taken to change position, I can find the average velocity of an object. The average acceleration is defined as the change in velocity. So velocity change in position, acceleration change in velocity. Acceleration is said to be the second derivative of position with respect to time. And velocity and acceleration are words that you will hear, all the time in everyday language. People talk about velocity, people talk about acceleration. If I go further down, the average jerk is defined as the change in acceleration. So velocity change in position, acceleration change in velocity, jerk change in acceleration divided by the change in time. This is its little formula here. Average jerk equals change in acceleration divided by the change in time. And again, it's one of those little triangular relationships. The average jerk is change in acceleration divided by change in time. So suppose I'm given here an initial acceleration of 1 meter per second squared and a final acceleration of 3 meters per second squared, and 4 seconds of time passed while changing my acceleration. We would say the average jerk here is equal to the change in acceleration, well, that's the final minus the initial, divided by the change in time. Now if I just think about the units here, on the top the units are meters per second squared, and on the bottom we have seconds. 3 subtract 1 is 2, 2 divided by 4, well, that's a half. Meters per second squared divided by seconds, they're called meters per second cubed. So the average jerk here of this object is a half a meter per second cubed. So we get jerk from acceleration. It's the derivative of acceleration. And we say the jerk is the third derivative of position with respect to time. First derivative of position, velocity. Second derivative of position, acceleration. Third derivative of position is jerk. And if I take another derivative, the next one is called snap. Snap is defined as the change in jerk divided by the change in time. Again, you see these things. It's the formulas, hopefully, are looking pretty much the same every time. So to find the average snap, and we have to be a little bit careful here. I'm using an S here for snap, but we don't want to confuse that with our letter we use for displacement. So we would say it's the change in jerk divided by the change in time. So if the final jerk is 1 and the initial jerk is -1, we've got 1 subtract -1 will be the change in jerk. Notice the units there will be meters per second cubed. And on the bottom, we've got 2 seconds of time have passed. 1 subtract -1 is +2. We've got 2 divided by 2, which is 1. And my units here now are meters per second to the power 4. And that's my average snap. That's the average snap. Notice the exponent on the seconds here are growing all the time. So snap is said to be the fourth derivative of position with respect to time. Position, velocity is the first derivative, acceleration second, jerk is the third derivative, and snap is the fourth derivative. Notice fourth derivative giving me a little degree 4 there on my S under the bar. Crackle. Average crackle is defined as being the change in snap divided by the change in time. Again, same thing. It's the same thing pretty much all the time. If I want to find the average crackle here, well, it's the change in snap, which will be the final snap here of 4. Subtract the initial snap of 10, all divided by 6. I'll leave the units out here until my final answer. And 4 subtract 10, that's -6. -6 divided by 6, that's -1. And in this case, we're talking about meters per second to the power 4 divided by seconds. That's going to be meters per second to the power 5. So crackle is said to be the fifth derivative of position with respect to time. The next derivative is called pop. And pop is defined as the change in Crackle divided by the change in time. Over 5 seconds, the average pop of a particle is 3 meters per second to the power of 6. If the initial Crackle was negative 2 meters per second to the power of 5, what is the final Crackle? Well, again, if I think about my equation as one of these silly triangles, average pop, change in Crackle over change in time, what I can work out is that the change in Crackle is always going to be the average pop multiplied by the change in time. Here the average pop is given as 3. The change in time is 5. And if I think about the units here, let me actually put the units in this case. So it's 3 meters per second to the power of 6. Meters per second, apologies. Meters per second to the power of 6. And that's multiplied by the change in time, which is 5 seconds. So what I'm going to get, 3 by 5, giving me 15. And this second here will cancel with one of these to give me meters per second to the power of 5. So the change in Crackle here is going to be 15 meters per second power of 5. Positive, so it's increase. So the change in Crackle is an increase of 15 meters per second to the power of 5. If the initial Crackle was negative 2, well, my final Crackle is going to be my initial Crackle, negative 2, plus my increase of 15. So it's going to be 13 meters per second to the power of 5. Okay, notice here we're talking about the change, average pop. Pop is the change in Crackle divided by the change in time. And pop is said to be the 6th derivative of position with respect to time. Notice the units for pop, 3 meters per second power of 6. The derivative of pop is called lock, and lock is said to be the 7th derivative of position with respect to time. Over 10 seconds, the average lock of a particle is negative 3 meters per second power of 7. If the initial pop was 30 meters per second power of 6, then what was the final pop? And again, think about this as one of these silly triangles. Change in pop, average lock, change in time. So I can find the change in pop by multiplying the average lock by the change in time. The average lock was negative 3. That's meters per second to the power of 7. I'm multiplying it by the change in time, which is 10 seconds. The units, one of those, we cancel with that second. Negative 10 times 3, that's, let me write it down here, negative 30. That's going to be meters per second to the power of 6. Notice negative, that's a decrease of 30 meters per second to the power of 6. So what happens over this 10 seconds is the pop decreases by 30 meters per second to the power of 6. So my final pop, P sub f, P final, well, my initial pop was positive 30, and then it's decreased by 30. And so my final pop is 0 meters per second to the power of 6. Okay, so lock, this thing here, lock is said to be the 7th derivative, and lock gets these units, meters per second to the power of 7. And the last derivative I'll look at is drop. Drop is said to be the 8th derivative of position with respect to time. And there's its equation. Notice you can always draw a silly triangle from one of these little relationships. Change in lock, change in time gives me my average drop. Okay, over 2 seconds, the average drop of a particle is 3 meters per second to the power of 8. If the initial lock was negative 1 meter per second to the power of 7, then what was the final lock? Okay, the initial lock. So the change in lock is going to be my average drop times my change in time. My average drop here is 3 meters per second to the power of 8. My change in time here is 2 seconds. 3 2s are 6. What will happen here is our units, one of those 8 will cancel with that to give me seconds to the power of 7. So my change in lock is 6 meters per second. Notice it's positive. That's an increase of 6 meters per second to the power of 7. So my final lock, L final, is going to be my initial lock, -1. And it's then increased by 6. My units are going to be meters per second to the power of 7. So that's going to be 5 meters per second to the power of 7. Much harder to visualize, what these things mean. But, for our purposes, all we're talking about is different derivatives of position. Drop is said to be the 8th derivative of position. So velocity is the first derivative of position, acceleration is the second, jerk is the third, snap is the fourth, crackle is the fifth, pop is the sixth, lock is the seventh, and drop is the 8th derivative of position with respect to time.